Okay, so I said there's two ways that we're going to usually solve these total power situations. If I have these boxes, then essentially I have a P and a Q inside of each box. And so in order to get my S total, I'm just going to add up my S1, S2 of all these complex powers. Well, how do I add up the vectors? The best way to do it is in rectangular. So it's like I'm doing P1, P2, P3, P4, and I'm summing those up, and I'm doing Q of each of these, right? So 1, 2, 3, 4. These are the vectors. And so all I'm doing, and the way I'm writing it is kind of like old school, back to elementary school, I'm just adding up all of these vectors. Over on the left, though, I'll actually write what they are. So P1, if this is 1, 2, 3, and 4, P1 is 4. P2 is 0. I have 6 kVAR, which is a Q, and my power factor is 0. So if the power factor of 1 is all real, a power factor of 0 is all reactive. But it says it's lagging, so this in a second will mean that it's inductive. This one also says 3 says 0, and then right here is 2. So my P total in this case is 6 kilowatts. My Q total, Q of the first one is 0 kVAR, which that kind of tells me by that it's inside that box is just a resistor. It's all real, nothing reactive. The second one is positive 6 because this is lagging, which means it's inductive, right? The third one is kVAR, it's capacitive, so that's negative, minus 2. And then this one says the power factor is at 1. So that one's a resistor, that one's an inductor, and this one is a capacitor. These are all just pure elements. Now, if I did have a box that said something like, 2 watts, 2 VAR, well, that would mean that inside that box, there's a resistor and a capacitor, or a resistor and an inductor, depending on how it was labeled, capacitive or inductive, right? And so there's other ways that we could do that. We could give you a power factor. If it's anything but 1 or 0, then there's kind of 2 elements inside that box. As it is, all of these are just pure elements. And that last one, it's at 0. So this together makes 4 k VAR. And I'll label it as inductive just to be clear. If it's positive, it means it's inductive. And I can even already tell you right now, that Q is what's going inside of here, the reactive power to bring it to unity, but let's finish out the top. So we have a P and we have a Q. So if I'm drawing a power triangle, I have a P of 6 plus J4, there's 4, and then here's my power triangle. So what I need here is S. This is kilowatts, kVAR. I need my S and my angle. Well, the best way to do that is just to go from rectangular to polar. You could do 6 squared plus 4 squared and take its square root. You could do tangent, inverse tangent of one over the other, but the easiest way is to just go from rectangular to polar. So if I'm going from rectangular to polar, I get 7.21 kVA. And what we're looking at is S as a vector, 7.21 kVA, angle 33.68 degrees. So this right here is my apparent power S. S equals 7.21 kVA. The angle is 33.68. So what I have here is I have a power triangle. So when it says calculate and draw the total power triangle, here is my total power triangle. So now what we need to do is we want to cancel out that Q of 4. And the way we're going to do that, I'll draw it in green, is it's like we're adding in a new perfectly Q vector going down of -4. And once I do that, then S and P will be equal to each other. My theta will go to 0, my Q total will go to 0, and my power factor will go to unity. right? So we're adding in a -4. So the two ways to write that, you could either write -4 kVAR, or usually how I write it is 4 kVAR, lowercase cap, telling me it's capacitive. And so that capacitive will cancel out the inductive that was in the original power triangle. So the reactance that would do that, Q is equal to V squared over X. Right? I have a Q, I have a voltage that was 240, and I'm going to solve for a reactance X. I just use the absolute values because that's all that you need. 240 squared divided by Q, I'm just rearranging it. 240 squared divided by 4,000. Some people will write it with the -4,000 in there, but if that's the case, then you would need your initial equation to say negative V squared XC, because we're solving for a capacitive. I just use the absolute values. And also note about absolute values is that the magnitude V is all that we're taking. Well, in this case, that V up in the circuit, it already started at 0, so it wouldn't matter. But if you had an angle there, you would need to just take its magnitude. And that comes out to 14.4 ohms. And so the component that I'll need to put in here is I will need to put in a capacitor, right? In my capacitor equation, the reactance of a capacitor is 1/2 pi F capacitance. So I rearrange for capacitance, and I have 1/2 pi F XC, 1/2 pi 50, 14.4, and my final capacitance is 221, basically 0.0, 221 microfarads. And if I were to connect that in parallel to the total load, in this case, I would want to draw it right here to put it in parallel with the total load.